Hello there, and welcome to the Sleepless Scientist. Tonight, we're traveling far beyond our world, beyond our sun, beyond even the boundaries of our cosmic neighborhood. We're journeying through galaxies, vast islands of stars, gas and mystery scattered across the universe, like jewels in an endless dark sea. Each one holds billions of stars, each with its own story. Some are spiraling and young, others are ancient and still. Together, they map the history of everything that is, was, or ever will be. So settle in, let your thoughts drift outward, and join me as we explore these magnificent structures that fill the cosmos. And just before we begin, if these calm, curious explorations help you unwind, or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too. One sleepy soul at a time. The story of the universe begins. In the beginning, there was nothing. Then about 13.8 billion years ago, everything exploded into existence. We call it the Big Bang, though it wasn't an explosion in the traditional sense. Space itself began expanding, carrying energy and matter outward. For the first few 100,000 years, the universe was too hot for atoms to form. It was a glowing fog of particles and light, opaque and featureless. Then it cooled. Electrons joined with protons to form hydrogen, and suddenly, the universe became transparent. Light could travel freely for the first time. What followed was the cosmic dark ages, a long period when the universe was mostly hydrogen gas, spread thin across expanding space. There were no stars yet, no galaxies, just darkness and potential. Gravity began its slow work, pulling gas together into denser regions. These regions would become the seeds of the first galaxies. The story of galaxies is the story of structure emerging from chaos, of light returning to a darkened cosmos, of the universe learning how to shine. What is a galaxy? A galaxy is a vast collection of stars, gas, dust, and dark matter, all bound together by gravity. Think of it as a city of stars, containing millions, billions, or even trillions of suns. Each star follows its own orbit, moving through space in patterns shaped by gravity. Some galaxies are small and sparse, others are enormous, sprawling across hundreds of thousands of light years. They come in different shapes: spirals with graceful arms, ellipticals that glow softly, irregulars with no clear structure. But all share one thing: they're held together by invisible forces. Dark matter, which we can't see but can detect through its gravitational effects, makes up most of a galaxy's mass. The visible stars and gas are just the tip of the iceberg. Galaxies aren't static. They rotate, evolve, collide, and merge. They birth new stars and watch old ones die. They're dynamic, living systems on a timescale so vast we can barely comprehend it. And scattered across the universe, there are more galaxies than there are stars in our own. Each one is a world unto itself. The birth of the first galaxies. The first galaxies formed a few 100 million years after the Big Bang, emerging from the cosmic dark ages. Gravity pulled together dense clouds of hydrogen gas, concentrating them into regions where stars could finally ignite. These early galaxies were small, chaotic, and intense. Nothing like the grand spirals we see today. They were irregularly shaped, turbulent, and filled with massive short-lived stars that burned bright and died young. These first stars, called population 3 stars, were made of pure hydrogen and helium. When they exploded as supernovae, they scattered heavier elements into space: carbon, oxygen, iron, seeding the universe with the building blocks of future generations. The early galaxies merged frequently, colliding and blending into larger structures. It was a violent, creative era, a cosmic construction site where the universe was assembling its architecture. Over time, these small galaxies grew, combining and evolving into the diverse forms we observe today. The birth of galaxies marked the end of darkness and the beginning of the universe as we know it, a cosmos filled with light, complexity, and endless variation. Clouds of gas, becoming stars. Inside those early galaxies, something remarkable was happening. Clouds of gas, mostly hydrogen, began collapsing under their own gravity. As they contracted, they heated up. Pressure and temperature rose at the core. Eventually, conditions became extreme enough for nuclear fusion to begin. Hydrogen atoms fusing into helium, releasing tremendous energy. A star was born. This process continues today. Wherever there's a dense cloud of gas in the right conditions, stars can form. In galaxies, these star-forming regions glow brightly, illuminated by the young, hot stars within. The newborns are often massive and blue, burning their fuel rapidly. Around them, leftover gas and dust might coalesce into planets, moons, asteroids. The transformation from gas to star is alchemy on a cosmic scale, turning simple elements into radiant furnaces that light the universe. And it all begins with gravity, that patient, relentless force pulling matter together, creating order from chaos. Each star represents a new chapter, a new possibility, and galaxies are the stages where these stories unfold. The young universe takes shape. As the first billion years passed, the universe transformed. Small galaxies merged into larger ones. Gravity drew them together, creating clusters and eventually superclusters. The cosmic web began to take form, a vast network of filaments, nodes, and voids stretching across space. Along the filaments, galaxies gathered like beads on a string. In the nodes, massive clusters formed, containing thousands of galaxies bound by their collective gravity. Between them lay the voids, vast empty regions where few galaxies ventured. This structure wasn't random. It emerged from tiny quantum fluctuations in the early universe, amplified by gravity over billions of years. The young universe was taking shape, organizing itself into the patterns we observe today. Galaxies weren't isolated islands. They were part of a larger tapestry, connected by invisible threads of dark matter. And as time passed, this cosmic web grew more complex, more intricate. Stars formed, died, and scattered their ashes. Black holes grew at galactic centers. The universe was maturing, evolving from its chaotic youth into the structured cosmos we inhabit now. How gravity shapes galaxies. Gravity is the architect of galaxies. It pulls gas together to form stars. It holds those stars in orbit around the galactic center. It attracts neighboring galaxies, sometimes drawing them into collisions. Without gravity, galaxies would simply disperse, their stars drifting apart into the void. But gravity is patient and persistent. It works over millions and billions of years, slowly sculpting structure from randomness. Dark matter plays a crucial role. Though invisible, it outweighs ordinary matter 5 to 1. Its gravity creates wells, deep gravitational pits, where normal matter collects. These dark matter halos extend far beyond the visible edges of galaxies, providing the gravitational scaffolding that holds everything together. As galaxies rotate, gravity keeps stars in their orbits, preventing them from flying off into space. When galaxies collide, gravity orchestrates the merger, pulling them together over hundreds of millions of years. It's a force we barely notice in daily life. Drop something, and it falls. But on cosmic scales, gravity is everything. It's the sculptor, the conductor, the invisible hand shaping the universe. Every galaxy owes its existence to gravity's relentless pull. The beauty of spiral galaxies. Spiral galaxies are among the most beautiful structures in the universe. Picture a flattened disk with graceful arms, spiraling outward from a bright central bulge. Our Milky Way is a spiral, as is Andromeda. The arms aren't solid structures, they're density waves, regions where stars, gas, and dust temporarily crowd together. As material moves through these waves, it compresses, triggering star formation. That's why spiral arms glow so brightly. They're filled with young, hot stars and glowing nebulae. The central bulge contains older stars, densely packed and orbiting the galactic core. Surrounding everything is a halo of ancient stars and globular clusters. Spiral galaxies rotate, though not like a solid wheel. Stars closer to the center orbit faster, while those farther out move more slowly. This differential rotation would wind the arms tighter over time if they were physical structures, but since they're density waves, they persist. Spiral galaxies are dynamic, elegant, and alive with star formation. They represent galaxies in their prime, actively creating new stars, evolving and shaping their futures. They're cosmic works of art, painted in starlight. The power of elliptical galaxies. Elliptical galaxies are different, older, calmer, more subdued. They range from nearly spherical to elongated ellipses, glowing with a smooth, even light. There are no spiral arms, no prominent dust lanes, no bright regions of star formation. Instead, ellipticals are dominated by old red stars that orbit randomly, rather than in an organized disk. These galaxies form through mergers, the result of two or more galaxies colliding and blending over time. The collision scrambles the orbits, erasing any spiral structure and leaving a featureless, ellipsoidal shape. Elliptical galaxies come in many sizes. Some are small dwarfs, others are massive giants, the largest galaxies in the universe, containing trillions of stars. They reside at the centers of galaxy clusters, having consumed many smaller neighbors. Despite their calm appearance, ellipticals often harbor supermassive black holes at their cores, and some emit powerful jets of energy. They're not dead, just mature, galaxies that have settled into old age, their star-forming days mostly behind them. They glow softly, patiently, reminders that even galaxies grow old and quiet with time. The mystery of irregular galaxies. Not all galaxies fit neat categories. Irregular galaxies have no defined shape, no spiral arms, no smooth elliptical glow. They're chaotic, messy, and often small. The large and small Magellanic Clouds, satellite galaxies orbiting the Milky Way, are irregulars. They're rich in gas and dust, actively forming stars despite their disorganized appearance. What causes a galaxy to be irregular? Often, it's gravitational interactions. A close encounter with a larger galaxy can distort structure, pulling stars and gas into unusual configurations. Some irregulars may be young galaxies still forming, not yet settled into a recognizable shape. Others are the remnants of collisions, galaxies torn apart and reassembled into new, strange forms. Irregular galaxies challenge our classifications. They remind us that the universe doesn't always follow tidy rules. They're unpredictable, diverse, and fascinating precisely because they refuse to conform. In their chaos, there's beauty, a different kind of elegance, found not in symmetry, but in complexity. They're the wild children of the galactic family, defying expectations and charting their own paths through the cosmos. The Milky Way, our galactic home. Look up on a clear, dark night, and you might see it, a faint, milky band stretching across the sky. That's our galaxy, the Milky Way, seen from the inside. We live within a vast spiral galaxy, containing between 200 and 400 billion stars. Our Sun is just one of them, located about 26,000 light-years from the galactic center, out in one of the spiral arms. From our vantage point, we see the galaxy edge on, which is why it appears as a band. The Milky Way is roughly 100,000 light-years across, and about 1,000 light-years thick in most places. It rotates, taking our Sun about 225 million years to complete one orbit, a galactic year. The galaxy isn't alone. It's surrounded by dozens of smaller satellite galaxies, held by gravity, slowly being consumed, and it's part of a larger structure, the Local Group, which includes Andromeda and dozens of other galaxies. The Milky Way is our home on the largest scale we can imagine. Everything humanity has ever known exists within this one galaxy, and yet, it's just one among billions, a single note in the cosmic symphony. The heart of the Milky Way. At the very center of the Milky Way lies something extraordinary, a region dense with stars, gas, and intense gravitational forces. This is the galactic core, a crowded, chaotic place, unlike anywhere else in the galaxy. Stars here orbit in tightly packed clusters, their light blending into a continuous glow, but the core holds a secret even more profound. Deep within, there's a supermassive black hole, a gravitational monster with a mass of about 4 million suns. We call it Sagittarius A*, and though we can't see it directly, black holes emit no light. We can observe its effects. Stars orbit around it at incredible speeds, completing circuits in just years or decades. Their motion reveals the black hole's presence and allows us to measure its mass. The core is also a source of powerful radiation and magnetic fields shaped by the black hole's influence. It's a dynamic, violent place, a reminder that even the most serene-looking galaxies harbor immense power at their hearts. The galactic center is both beautiful and dangerous, a place where gravity reigns supreme. The supermassive black hole within. Supermassive black holes exist at the centers of most large galaxies, and the Milky Way is no exception. Sagittarius A*, formed billions of years ago, likely from the collapse of massive gas clouds or the merger of smaller black holes. It's grown over time by consuming stars, gas, and anything that ventures too close. The event horizon, the point of no return, is about 12 million miles across, roughly the distance from the Sun to Mercury's orbit. Beyond that boundary, nothing can escape, not even light. Around the black hole, an accretion disk of superheated material swirls inward, glowing brightly before disappearing forever. But Sagittarius A*, is relatively quiet compared to some supermassive black holes. It's not actively feeding on large amounts of material, so it doesn't emit the intense radiation seen in more active galaxies. Still, its gravity dominates the core, controlling the orbits of stars within several light years. Studying black holes like this teaches us about gravity, space-time, and the extremes of physics. They're nature's ultimate laboratories, places where the rules of the universe are pushed to their limits. Stars that circle the core. Near the galactic center, stars orbit in a cosmic dance. These aren't ordinary stars. They're some of the fastest moving stars known, whipping around the supermassive black hole at incredible speeds. Some complete their orbits in just a few years, reaching velocities of thousands of miles per second. By tracking these stars over time, astronomers can map their orbits with precision. The motion is purely gravitational, following the same laws that govern planets orbiting the Sun, but on a far grander scale. These observations provided some of the strongest evidence for the existence of Sagittarius A*. The star's orbits couldn't be explained by anything other than an enormous invisible mass, a black hole. It's a testament to the power of observation and patience. Astronomers have watched these stars for decades, documenting their paths year after year. And from those painstaking measurements, they've revealed one of the galaxy's greatest secrets. The stars circle endlessly, messengers bringing news from the heart of the Milky Way, telling us stories of gravity, time, and the hidden forces that shape the cosmos. The galactic disk and its arms. Beyond the core lies the galactic disk, a vast, flattened structure where most of the Milky Way's stars reside. This disk is organized into spiral arms, though their exact number and structure are still debated. We think there are 4 major arms: Perseus, Sagittarius, Centaurus, and Scutum Centaurus, curving outward from the center. Our Sun sits near the inner edge of the Orion arm, a smaller spur between 2 major arms. The arms aren't solid. They're regions of higher density, where stars, gas, and dust concentrate. As material moves through these density waves, it slows down, creating a traffic jam of sorts. This compression triggers star formation, which is why spiral arms glow so brightly. The disk rotates differentially, inner regions faster, outer regions slower. This creates the spiral pattern, a beautiful example of physics and dynamics on display. The disk is thin, just 1,000 light years thick in most places. But it's where the action happens, where new stars are born, where planets form, where life, at least in one small corner, has emerged. Where new stars are born. Star formation happens in specific regions of the galaxy, cold, dense clouds of gas and dust, where gravity can collapse material into new suns. These molecular clouds are scattered throughout the galactic disk, especially in the spiral arms. They're vast, sometimes hundreds of light years across, and they contain enough material to form thousands or millions of stars. Inside these clouds, gravity pulls gas into clumps. When a clump becomes dense and hot enough, nuclear fusion ignites, and a star is born. Often, stars form in clusters, dozens or hundreds at once, from the same cloud. The Pleiades, visible to the naked eye, is one such cluster, still young and loosely bound. Star formation isn't constant. It comes in bursts, triggered by events like nearby supernova shock waves or the passage through a spiral arms density wave. These triggers compress the gas, initiating collapse. Without them, clouds might remain stable indefinitely. The birth of stars is the galaxy's way of renewing itself, creating new generations to replace those that have died. It's a cycle as old as the galaxy itself. Nebulae, the cradles of creation. Nebulae are among the most beautiful sights in the galaxy. Glowing clouds of gas and dust, illuminated by the stars within or nearby. Some, like the Orion Nebula, are star-forming regions, stellar nurseries, where new suns are being born. These emission nebulae glow red and pink, lit by ultraviolet light from hot young stars that ionize the surrounding hydrogen. Other nebulae are remnants, the remains of stars that have died. Planetary nebulae, despite their name, have nothing to do with planets. They form when sun-like stars shed their outer layers at the end of their lives, creating expanding shells of gas. The Ring Nebula and the Helix Nebula are famous examples. Then there are supernova remnants, chaotic structures left behind when massive stars explode. The Crab Nebula is one, still expanding over 950 years after the explosion that created it. Nebulae are transient, existing for only a cosmically brief moment before dispersing. But in that moment, they're radiant, glowing testaments to the cycle of stellar life and death. They're the galaxy's gardens, places where endings and beginnings intertwine. The dance of dust and light. Dust might sound mundane, but in space, it's anything but. Cosmic dust consists of tiny particles, grains of carbon, silicon, iron, and other elements, scattered throughout the galaxy. These particles are incredibly small, often just a fraction of a micron across. Yet collectively, they play a vital role. Dust absorbs starlight, dimming and reddening it. Dark nebulae, like the Horsehead Nebula, are dense clouds of dust that block light from stars behind them, appearing as dark silhouettes against brighter backgrounds. But dust also radiates energy. Heated by starlight, it glows in infrared wavelengths, invisible to our eyes, but detectable by specialized telescopes. Dust is essential for star and planet formation. It provides surfaces where molecules can form and stick together, building larger structures. Without dust, planets like Earth might never have formed. And dust creates some of the galaxy's most stunning visual features. The dark lanes and spiral arms, the intricate filaments and nebulae. It's a reminder that even the smallest components can have profound effects, shaping the cosmos in unseen but essential ways. Star clusters in the galactic halo. Surrounding the galactic disk is the halo, a roughly spherical region containing old stars and globular clusters. Globular clusters are dense, spherical collections of stars, each containing hundreds of thousands to millions of suns packed into a relatively small space. They're ancient, among the oldest structures in the galaxy, formed over 10 billion years ago. Their stars are metal poor, meaning they contain few elements heavier than hydrogen and helium, a sign they formed early, before supernovae enriched the galaxy with heavier elements. These clusters orbit the galactic center on elongated paths, sometimes passing through the disk, but spending most of their time in the halo. They're relics, fossils from the galaxy's youth, preserved largely unchanged. Studying them gives astronomers clues about the conditions in the early universe and the history of galaxy formation. The halo also contains individual stars, scattered sparsely compared to the disk. These are often old as well, remnants of smaller galaxies that the Milky Way consumed long ago. The halo is quieter, more diffuse, a ghostly reminder of the galaxy's ancient past. Ancient stars and cosmic history. The oldest stars in the Milky Way are time capsules, carrying information about the galaxy's earliest days. Some are over 13 billion years old, formed when the universe was still young. These stars are metal poor, containing almost pure hydrogen and helium from the Big Bang, with only traces of heavier elements. By studying their composition, astronomers can learn about the conditions in the early universe and the processes that created the first elements. Ancient stars also tell us about galactic evolution. Many reside in the halo, or in globular clusters, suggesting they formed before the disk assembled. Some were likely born in smaller galaxies that merged with the Milky Way, their stars now incorporated into our galaxy. Finding and studying these ancient stars is challenging. They're faint, often hidden among brighter, younger stars, but each one discovered adds a piece to the puzzle of cosmic history. They're witnesses to events that happened billions of years ago, living records of a universe we can no longer see directly. In their light, faint and ancient, we glimpse the past. The motion of the Milky Way. Galaxies don't sit still. The Milky Way is in constant motion, traveling through space at about 370 miles per second, relative to the cosmic microwave background. That's over 1,000,000 miles per hour. Part of that motion is the galaxy's rotation. Stars orbiting the galactic center, including our Sun, which takes 225 million years to complete one orbit. But the galaxy itself is also moving, pulled by the gravitational attraction of other galaxies and the larger structures of the cosmic web. We're being drawn toward the Virgo supercluster, a massive collection of galaxies, about 65 million light-years away. And beyond that, there's an even larger structure, sometimes called the Great Attractor, exerting its gravitational pull. These motions are imperceptible on human timescales, but over millions and billions of years, they reshape the universe. Galaxies drift, collide, merge. The Milky Way's motion is part of a cosmic ballet, a slow dance choreographed by gravity, playing out across billions of light years. We're passengers on this journey, orbiting a star that's orbiting a galaxy that's hurtling through space. Our place in the galactic map, mapping our position in the Milky Way, has been surprisingly difficult. We're inside the galaxy, surrounded by stars and dust that obscure our view. It's like trying to map a city from the middle of a crowded street. But over decades, astronomers have pieced together a picture. We're in the Orion Arm, a minor spiral arm, about 26,000 light-years from the galactic center. Above and below the galactic plane, out of the crowded disk, we have a clearer view. That's where we find globular clusters and other galaxies. Within the disk, dust blocks much of the visible light, especially toward the galactic center. But infrared and radio telescopes can peer through the dust, revealing the galaxy's structure. We now know the Milky Way is a barred spiral, with a central bar-shaped structure from which the spiral arms emerge. This bar rotates, influencing the motion of stars and gas throughout the inner galaxy. Our position is fortunate, far enough from the chaotic core to be relatively safe, but not so far out that we're isolated. We're in a suburban neighborhood of the galaxy, a comfortable spot to call home. The local group of galaxies. The Milky Way isn't alone in its corner of the universe. It's part of a small cluster called the local group. containing about 80 galaxies. Most are dwarfs, small and faint, with just millions of stars. But two galaxies dominate the group, the Milky Way and Andromeda. Together, they account for most of the group's mass and gravitational influence. The local group spans about 10 million light-years across. Other notable members include the Triangulum Galaxy, a smaller spiral, and the Magellanic Clouds, satellite galaxies visible from the southern hemisphere. These galaxies are bound together by gravity, orbiting a common center of mass somewhere between the Milky Way and Andromeda. Over time, the group's structure has evolved. Smaller galaxies have been captured by the larger ones, their stars absorbed. The Milky Way has consumed several dwarf galaxies and is currently in the process of devouring others. The local group is our cosmic neighborhood, a small collection of galaxies isolated from other groups and clusters by vast stretches of empty space. It's home, on the largest scale we can meaningfully grasp. Our neighbor, the Andromeda Galaxy. Just 2.5 million light-years away lies Andromeda, the nearest large galaxy to the Milky Way. It's a spiral, slightly larger and more massive than our own galaxy, containing perhaps 1 trillion stars. On a dark night, away from city lights, you can see Andromeda with the naked eye, a faint fuzzy patch in the constellation of the same name. That light began its journey 2.5 million years ago, when our ancestors were just beginning to walk upright. Andromeda is beautiful, a grand spiral with well-defined arms, a bright central bulge, and a halo of globular clusters. It's similar to the Milky Way in structure, though observations suggest it may have undergone more mergers in its past. Like our galaxy, Andromeda harbors a supermassive black hole at its core, even more massive than Sagittarius A*. The two galaxies are approaching each other, drawn together by mutual gravitational attraction. In about 4.5 billion years, they'll collide, but that's a story for another moment. For now, Andromeda is a neighbor, a companion galaxy, sharing our small corner of the universe, a reminder that even galaxies don't exist in isolation. The future collision of Milky Way and Andromeda. In roughly 4.5 billion years, something remarkable will happen. The Milky Way and Andromeda will collide. Don't worry. Collisions between individual stars are almost impossible. Space is vast, and stars are tiny, but the galaxy's gravitational fields will interact, pulling stars and gas into new configurations. The collision will unfold over hundreds of millions of years. At first, the galaxies will approach, their spiral arms beginning to distort. Tidal forces will stretch and warp both structures. Gas clouds will collide, triggering intense bursts of star formation. The night sky, for any observers present, will be spectacular. Two galactic cores growing closer, spiral arms tangling, new stars igniting. Eventually, the galaxies will pass through each other, then swing back for another pass. Gravity will gradually blend them, erasing their separate identities. Stars will be scattered into new orbits, some flung out into intergalactic space, others pulled toward the merging cores. It will be chaos, but beautiful chaos, a cosmic dance that transforms two galaxies into one. And from that collision, something new will emerge. What will happen when they merge? The merger of the Milky Way and Andromeda will create a new galaxy, probably an elliptical, given the violence and randomness of the collision. The once elegant spiral structures will be scrambled, their orderly rotation replaced by stars moving in random directions. The new galaxy will be larger and more massive than either predecessor. Astronomers have even given it a name, Milky Way. During the merger, star formation will spike as gas clouds collide and compress. But over time, most of the gas will either form stars or be heated and blown out of the galaxy by supernovae and stellar winds. Eventually, star formation will slow and then cease. Milky Way will settle into a quiet old age, a galaxy of aging red stars with little new activity. The supermassive black holes at the centers of both galaxies will spiral inward, eventually merging into a single, even more massive black hole. This event will release gravitational waves, ripples in space-time detectable across the universe. By the time this happens, the Sun will likely be in its red giant phase, possibly having already engulfed Earth. But somewhere in Milky Way, life might witness the aftermath. The Triangulum Galaxy's role. The Triangulum Galaxy, also called Me-33, is the third largest member of the local group. Though much smaller than the Milky Way or Andromeda, it's a beautiful spiral, face-on from our perspective, about 3 million light-years away. Triangulum contains perhaps 40 billion stars, significant but modest compared to its larger neighbors. It's been suggested that Triangulum is gravitationally bound to Andromeda, possibly orbiting it. If so, it will be caught up in the eventual collision. The three-way interaction could be complex, with Triangulum either merging with the combined Milky Way-Andromeda system or being flung outward by gravitational interactions. Some simulations suggest it might survive the encounter, though heavily distorted. Others predict it will be absorbed. Either way, Triangulum's fate is tied to the larger galaxies. It's a reminder that galaxies don't exist in isolation. They're part of dynamic systems, influenced by their neighbors. The local group isn't static, it's evolving, and billions of years from now, it will look very different. Triangulum is part of that story, a smaller player in a grand cosmic drama. Galaxies that collide and blend. Galactic collisions are common throughout the universe. Galaxies are gregarious. They form groups and clusters, drawn together by gravity, and when they get close enough, they collide and merge. These interactions unfold over hundreds of millions of years, far too slow for human eyes to perceive. But we can observe galaxies at different stages of collision, creating a sequence that reveals the process. Early-stage collisions show distorted spiral arms, tidal tails of stars and gas stretching between the galaxies. Mid-stage interactions feature chaotic, disturbed structures, intense star formation, and sometimes spectacular bridges of matter. Late-stage mergers show galaxies nearly blended, their cores spiraling inward, approaching the final coalescence. The result is often an elliptical galaxy, its orderly structure erased by the violence of the merger. But collisions aren't purely destructive. They trigger star formation, redistribute gas, and can rejuvenate aging galaxies. They're transformative events, reshaping galaxies and influencing their evolution. The universe's largest elliptical galaxies, formed through multiple mergers, consuming smaller neighbors over billions of years. Collisions are part of the cosmic life cycle, a process as natural as stars being born and dying. The glow of starburst galaxies. Some galaxies shine with unusual brilliance, glowing intensely in infrared light. These are starburst galaxies, undergoing episodes of extreme star formation, sometimes hundreds or thousands of times faster than normal. What triggers such intense activity? Often, it's a collision or close encounter with another galaxy. The gravitational interaction compresses gas clouds, triggering widespread star formation. The result is spectacular. Millions of massive stars born in a relatively short period, lighting up the galaxy. But this intensity can't last. The burst of star formation consumes gas rapidly, and massive stars live fast and die young, exploding as supernovae within a few million years. These supernovae, occurring in rapid succession, can heat and expel remaining gas, quenching further star formation. Starburst galaxies are transient, a brief, brilliant phase in galactic evolution. Observing them gives astronomers insight into what might have been common in the early universe, when galaxy collisions were more frequent. Their cosmic fireworks displays, intense and beautiful, reminding us that galaxies, like stars, have moments of spectacular brilliance before settling into calmer states. The calm of lenticular galaxies. Between spirals and ellipticals lie lenticular galaxies, lens-shaped systems with characteristics of both. They have a central bulge and a disk, like spirals, but no prominent spiral arms. And like ellipticals, they contain mostly old stars with little ongoing star formation. Lenticulars seem to be transitional, perhaps spirals that have exhausted their gas supply or ellipticals that retain some disk structure. They're common in galaxy clusters, where high-speed collisions and interactions can strip gas away, halting star formation. Without gas, spiral arms fade, leaving a smooth disk. Lenticular galaxies are calm, settled, and somewhat enigmatic. They don't fit neatly into categories, which makes them interesting. Their existence suggests galaxy evolution isn't a simple one-way path, but a complex process influenced by environment, interactions, and internal dynamics. Studying lenticulars helps astronomers understand how galaxies change over time, how they lose gas, and what factors determine their final forms. They're reminders that the universe is full of in-between states, galaxies that don't fit simple labels, but tell important stories about transformation and evolution. The hidden dwarfs of the universe. Dwarf galaxies are the universe's underdogs, small, faint, and easily overlooked. They contain just millions to a few billion stars, compared to hundreds of billions in large galaxies. Some are tiny, barely more than star clusters, yet dwarf galaxies outnumber large ones by a significant margin. The Milky Way alone has dozens of known dwarf satellite galaxies orbiting it, and more are discovered regularly. Many are so faint, they're only visible with sensitive telescopes. Dwarfs come in different types. Dwarf ellipticals and dwarf spheroidals are dominated by old stars with little gas. Dwarf irregulars are gas-rich and actively forming stars. Blue compact dwarfs are undergoing intense starbursts. Despite their size, dwarf galaxies are important. They're building blocks. Larger galaxies, like the Milky Way, formed partly by consuming dwarfs. They also provide insights into dark matter, as some dwarfs are dominated by it, containing far more dark matter than visible stars. The smallest, faintest dwarfs challenge our understanding of what constitutes a galaxy. They're reminders that size doesn't determine significance. Even the smallest galaxies play crucial roles in the cosmic story. Tiny galaxies with big stories. Some dwarf galaxies have outsized importance in astronomy. Take the Sagittarius dwarf elliptical galaxy, currently being torn apart and absorbed by the Milky Way. Its stars are scattered along a stream, wrapping around our galaxy, evidence of ongoing cannibalism. This galaxy has likely passed through the Milky Way's disk multiple times, each passage pulling more stars away. Or consider the Small Magellanic Cloud, a dwarf irregular visible from the southern hemisphere. It's one of the Milky Way's closest companions and has been interacting with our galaxy for billions of years. These interactions have triggered star formation in both galaxies, creating regions of bright young stars. Dwarf galaxies also help us study dark matter. Some contain so much dark matter, relative to normal matter, that they're almost invisible, detectable only through their gravitational effects on nearby objects. Others, like ultra-faint dwarfs, are the faintest galaxies known, containing just a few thousand stars. Each discovery adds to our understanding of galaxy formation, dark matter distribution, and the hierarchical way galaxies grow by absorbing smaller neighbors. These tiny galaxies remind us that cosmic history is written not just by giants, but by countless small players whose contributions accumulate over time. Every dwarf has a story, and together, those stories reveal the complex, interconnected nature of galactic evolution. The largest galaxies ever found. At the opposite extreme are the giant elliptical galaxies, monsters containing trillions of stars. ISI 1101, located over 1 billion light-years away, is one of the largest known. It spans about 6 million light-years across, roughly 60 times the diameter of the Milky Way. It contains an estimated 100 trillion stars, How do galaxies grow so enormous? Through mergers. These giants typically reside at the centers of massive galaxy clusters, where they've spent billions of years consuming neighbors. Each merger adds mass, and over time the central galaxy becomes dominant. These galaxies are often called brightest cluster galaxies, or BCGs. They're smooth, featureless ellipticals, glowing with the combined light of countless old red stars. At their cores lurk supermassive black holes of extraordinary mass, billions or even tens of billions of solar masses. Giant ellipticals are the end state of galactic evolution in dense environments, galaxies that have gorged themselves on their surroundings. They're impressive, but also sobering reminders of cosmic hierarchy, the strong consuming the weak, gravity favoring the already massive. Giants at the edge of the cosmos. Looking deep into space means looking back in time. Light from distant galaxies has traveled for billions of years to reach us, showing those galaxies as they appeared in the distant past. Some of the most distant galaxies observed are over 13 billion light-years away, visible when the universe was less than a billion years old. These early galaxies are small and irregular, intensely forming stars. They're building the first generation of large-scale structures, creating the seeds that will grow into modern galaxies. Observing these distant giants is challenging. They're incredibly faint, their light stretched into infrared wavelengths by cosmic expansion. It requires the most powerful telescopes, like the James Webb Space Telescope, to detect them. Each new observation pushes the boundary further, revealing galaxies from earlier epochs. These distant giants teach us about the universe's youth, about how quickly galaxies formed after the Big Bang, and about the conditions in the early cosmos. They're time capsules, frozen in the light that's been traveling toward us for eons, finally arriving to tell their ancient stories. The shape and structure of a galaxy. A galaxy's shape tells its history. Spiral galaxies, with their graceful arms and rotating disks, are younger, gas-rich systems, actively forming stars. The spiral pattern emerges from density waves rotating through the disk, organizing stars and gas into elegant structures. Elliptical galaxies are smooth and featureless, shaped by mergers that scrambled orderly motion into random orbits. Their stars move in all directions, creating a diffuse glow without structure. Irregular galaxies lack organization entirely, often young or disturbed by gravitational interactions. Then there are peculiar galaxies, systems that defy easy classification, often mid-collision or displaying unusual features. A galaxy's structure is determined by its formation history, its environment, and its interactions with neighbors. Isolated galaxies tend to maintain spiral structure longer. Cluster galaxies experience frequent interactions that transform them into ellipticals. The shape also affects future evolution. Spirals can keep forming stars as long as gas remains, while ellipticals, having exhausted their gas, grow old quietly. Structure and destiny are intertwined. Each galaxy's form a record of its past and a predictor of its future. How dark matter holds galaxies together. Visible matter, stars, gas, dust, makes up only about 15% of a galaxy's mass. The rest is dark matter, invisible and mysterious. We can't see it, but we know it's there through its gravitational effects. Stars in the outer regions of galaxies orbit faster than they should if only visible matter were present. They should fly off into space, but they don't. Something unseen holds them in place. Dark matter. It forms vast halos around galaxies, extending far beyond the visible edges. These halos provide the gravitational scaffolding that holds galaxies together. Without dark matter, galaxies as we know them couldn't exist. They'd either collapse into dense clusters or disperse into space. Dark matter also shaped the large-scale structure of the universe, its gravity pulling normal matter into the filaments and nodes of the cosmic web. Despite decades of searching, we still don't know what dark matter is made of. It doesn't interact with light or normal matter, except through gravity. It's one of the greatest mysteries in physics, a reminder that most of the universe remains hidden from our direct perception. The invisible web of the universe. On the largest scales, the universe is organized into a vast cosmic web, a network of filaments, walls, nodes, and voids. This structure formed over billions of years, shaped by gravity, acting on tiny density variations in the early universe. Dark matter, making up most of the universe's mass, collapsed first, creating gravitational wells where normal matter collected. Along the densest regions, matter accumulated into filaments, vast, thread-like structures stretching across hundreds of millions of light years. Where filaments intersect, massive galaxy clusters formed, containing thousands of galaxies. Between the filaments lie voids, immense, nearly empty regions where few galaxies exist. The cosmic web is like a sponge, with matter concentrated along the edges and emptiness within. This structure isn't random. It's a direct consequence of the initial conditions of the universe, amplified by billions of years of gravitational evolution. Observing the cosmic web helps astronomers understand dark matter, dark energy, and the fundamental physics governing the universe. It reveals patterns on scales so vast, they dwarf individual galaxies, reminding us that even galaxies are just small components of something far grander. How galaxies form cosmic clusters. Gravity draws galaxies together into groups and clusters. Small groups, like our local group, contain a few dozen galaxies. Larger clusters can contain thousands, all bound by their mutual gravitational attraction. The Virgo cluster, about 65 million light-years away, contains over 1,500 galaxies. At the cluster's center sits a giant elliptical galaxy, M87, which has consumed many neighbors. Clusters are the largest gravitationally bound structures in the universe. Within them, galaxies move at high speeds, hundreds or thousands of miles per second, held in orbit by the cluster's immense mass. Most of that mass is dark matter, forming a vast halo that dominates the cluster's gravity. The space between galaxies isn't empty. It contains hot gas, heated to tens of millions of degrees, emitting X-rays. This intracluster medium contains more normal matter than all the galaxies combined. Galaxy clusters are cosmic laboratories where astronomers study dark matter, hot gas physics, and galaxy evolution. In these dense environments, interactions are frequent, shaping galaxies and sometimes destroying them, pulling them apart through tidal forces or stripping away their gas. The Great Walls of Galaxies. On even larger scales than clusters, galaxies organize into superclusters and vast walls, sheet-like structures, hundreds of millions of light-years long. The Sloan Great Wall, discovered in 2003, stretches over 1.4 billion light-years across, one of the largest structures known. These walls form the edges of voids, concentrations of matter, outlining vast empty regions. They're not solid structures. Galaxies within them are still separated by millions of light-years, but they represent regions where matter is significantly more concentrated than average. The existence of such large structures challenged early cosmological models, which predicted a more uniform distribution at these scales. But observations confirmed them, and modern theories now account for their formation through gravitational collapse over billions of years. The Great Walls are visible only through careful mapping of galaxy positions across vast volumes of space. They reveal the universe's large-scale architecture, showing that structure exists on scales almost incomprehensibly large. They're the universe's grandest patterns, visible only when we step back and view the cosmos as a whole, appreciating its organization across billions of light years. The vast voids between them, between the filaments and walls, lie cosmic voids, immense regions where galaxies are rare or absent. These voids can span hundreds of millions of light years, containing far fewer galaxies than average. They're not completely empty. Some galaxies exist within them, usually small, isolated dwarfs, but they're dramatically underdense compared to surrounding regions. Voids formed naturally during cosmic evolution. As matter collapsed into denser regions, it left behind underdense areas that expanded as the universe grew. Galaxies within voids tend to be different, smaller, bluer, more actively forming stars. They've experienced fewer interactions and mergers, evolving more peacefully than their cluster-dwelling cousins. Voids are surprisingly regular in size and shape, often roughly spherical or ellipsoidal. They occupy most of the universe's volume, even though most galaxies reside in the filaments and clusters. Understanding voids helps astronomers test theories of cosmic structure formation and dark energy. They're sensitive to the expansion history of the universe, their sizes and distribution revealing information about the forces shaping cosmic evolution. Voids are the quiet spaces, the pauses between notes in the cosmic symphony, essential to the overall composition. Light traveling across billions of years. When we observe distant galaxies, we're seeing ancient light. A galaxy 1 billion light-years away appears as it was 1 billion years ago. The light we see today began its journey when the universe was younger, traveling across expanding space to finally reach our telescopes. This makes astronomy unique. It's time travel through observation. The farther we look, the further back we see. The most distant galaxies visible today appear as they were over 13 billion years ago, when the universe was young. Their light has been traveling almost since the beginning, crossing vast distances while the universe expanded around it. This expansion stretches the light, shifting it toward longer, redder wavelengths, a phenomenon called redshift. By measuring redshift, astronomers determine how far away a galaxy is and how long its light has traveled. Every galaxy we observe is a snapshot from a different moment in cosmic history. Nearby galaxies show the modern universe. Distant ones reveal the past. By studying galaxies at different distances, astronomers piece together the story of cosmic evolution, watching galaxies grow, merge, and change over billions of years. Light is our messenger, carrying news from across space and time, seeing the past through galaxies. Every galaxy is a time capsule. When we study a galaxy 10 billion light-years away, we see it as it was 10 billion years ago. Smaller, perhaps, more chaotic, forming stars intensely. Nearby galaxies, just millions of light-years away, show the modern era, mature structures, settled into recognizable forms. By comparing galaxies at different distances, astronomers construct a narrative of galactic evolution. Young galaxies were smaller, bluer, more irregular. They formed stars rapidly, building mass quickly. Over time, they grew through mergers and accretion. Star formation slowed in many, especially those in dense environments where gas was stripped away or heated. By 5 billion years ago, many large spirals and ellipticals had formed, resembling modern galaxies. Today's universe is more settled, less chaotic, with lower average star formation rates. This technique, studying objects at different distances to see different ages, is unique to astronomy. It allows us to watch evolution unfold, not in real time, but across cosmic history, captured in light still traveling toward us. Each galaxy is a window into a specific moment, and together they form a motion picture of the universe growing up. How telescopes reveal the distant universe. Telescopes are time machines. The larger and more sensitive they are, the farther, and therefore further back in time, they can see. Ground-based telescopes observe relatively nearby galaxies, studying structure and dynamics. Space telescopes, free from Earth's atmosphere, can detect fainter, more distant objects. The Hubble Space Telescope transformed our understanding of the distant universe. Its deep field images, staring at tiny patches of seemingly empty sky for days, revealed thousands of galaxies, some over 13 billion light-years away. Each tiny smudge represented an entire galaxy, seen in its youth. Now, the James Webb Space Telescope pushes even further. Its infrared vision penetrates dust and detects light from the earliest galaxies, formed just a few 100 million years after the Big Bang. These observations are rewriting our understanding of how quickly galaxies formed and how massive they became. Radio telescopes detect different signals: cold gas, radio emissions from active galactic nuclei. X-ray telescopes observe hot gas and energetic processes. Each wavelength reveals different aspects of galaxies, and together they create a complete picture. Telescopes are our eyes on the cosmos, extending our vision across space and time. The first galaxies ever observed. The first galaxies formed between 100 and 500 million years after the Big Bang, emerging from the cosmic dark ages. These earliest galaxies were small, perhaps just a few million solar masses, intensely forming stars from pristine hydrogen and helium. They were irregular, chaotic, and short-lived as independent entities. They quickly merged with neighbors, building larger structures. For decades, these first galaxies remained beyond our observational reach, too distant and faint. But the James Webb Space Telescope changed that. In 2022 and beyond, it detected galaxies from when the universe was just 300 to 400 million years old. Some of the earliest ever observed. They appear as tiny red dots, their light stretched into infrared by cosmic expansion. Some are surprisingly bright and massive, challenging theories about how quickly galaxies could form. These observations are providing the first direct look at galaxy birth, revealing how the universe transitioned from darkness to light. Each detection is precious, a glimpse into an era previously accessible only through theory and simulation. The first galaxies are no longer hypothetical. They're real objects we can study, analyze, and learn from. Discoveries from the James Webb Telescope. The James Webb Space Telescope has revolutionized our view of early galaxies. Its infrared vision, an enormous mirror, allow it to see further and more clearly than ever before. Among its discoveries are galaxies from less than 400 million years after the Big Bang, seeing them as they truly were in the universe's infancy. Some are more massive than expected, containing billions of solar masses worth of stars. This surprised astronomers, who thought galaxies grew more slowly. It suggests star formation in the early universe was extraordinarily efficient. Webb has also observed early galaxies in unprecedented detail, revealing structure, bars, clumps, even hints of spiral patterns, suggesting organization emerged earlier than thought. It's detected supermassive black holes in these early galaxies, raising questions about how such massive objects formed so quickly. And it's analyzed the light from these distant galaxies, revealing their chemical composition, showing that even early in cosmic history, stars had begun enriching the universe with heavy elements. Every image Webb returns is a treasure, pushing back the boundaries of the observable universe and challenging our understanding of galaxy formation. It's still early, but Webb is already rewriting textbooks. The colors of galaxies explained. Galaxies come in different colors, primarily red and blue, and these colors tell stories about their ages and activities. Blue galaxies are dominated by young, hot stars that emit most of their light in blue wavelengths. These galaxies are actively forming stars, with plenty of gas available. Blue is the color of youth and activity. Red galaxies, on the other hand, contain mostly old stars. Young, massive blue stars have already died, leaving behind smaller, cooler red stars that emit primarily in red wavelengths. Red galaxies have little star formation. They've exhausted their gas or had it stripped away. Red is the color of age and quiescence. Between blue and red lies the green valley, where galaxies transition from active to quiescent. This transition happens when star formation ceases, either because gas is consumed, blown away by stellar winds and supernovae, or stripped by interactions. Color is one of the first things astronomers measure when classifying galaxies. It immediately reveals whether a galaxy is young and growing or old and settled. And because color relates to star formation, it connects to galaxy evolution, environment, and destiny. Why some galaxies glow red or blue? A galaxy's color depends on its stellar population. If it's forming stars actively, massive blue stars dominate its light, making the galaxy appear blue. These stars are bright but short-lived, burning out in just millions of years. For a galaxy to stay blue, it must continuously form new stars to replace those that die. This requires a steady supply of cold gas. Blue galaxies are often spirals, rich in gas, with active star-forming regions in their disks. Red galaxies have ceased star formation. Without new massive stars, only smaller, longer-lived stars remain. These emit redder light, giving the galaxy its color. Why would star formation stop? Several reasons. A galaxy might exhaust its gas supply through intense star formation. Supernova explosions might heat and blow away remaining gas, or interactions with other galaxies, especially in dense clusters, might strip gas away through ram pressure or tidal forces. Once gas is gone, the galaxy reddens as massive stars die and aren't replaced. This transition is often irreversible. Red galaxies rarely become blue again unless they acquire new gas through mergers or accretion. Color is a proxy for life stage. Blue galaxies are in their prime, red ones in retirement. The role of hydrogen in galactic life. Hydrogen is the fuel of galaxies. It's the most abundant element, the raw material from which stars form. Galaxies are born with vast reservoirs of hydrogen gas, initially diffuse and spread throughout their volume. Over time, this gas cools and condenses into clouds, dense enough for gravity to collapse them into stars. Inside stars, hydrogen fuses into helium, releasing energy. When stars die, they return some material to space, but much is locked away or converted to heavier elements. Gradually, a galaxy's hydrogen supply dwindles. Star formation slows, eventually stopping when the gas is exhausted. But galaxies can replenish their hydrogen. They can accrete gas from the intergalactic medium, pulling in fresh fuel, or they can acquire it through mergers with gas-rich companions. Hydrogen isn't just fuel, it's also a tracer. Astronomers observe neutral hydrogen through its radio emission at 21 centimeters wavelength. Mapping this emission reveals gas distribution, rotation, and interactions. Hydrogen is fundamental to a galaxy's life cycle, determining how long it can form stars and how it evolves. Without hydrogen, galaxies fade into quiescence, their star-forming day is over. Supernovae shaping galaxies. When massive stars die, they explode as supernovae, events so bright they can briefly outshine entire galaxies. These explosions are violent, releasing as much energy in a few weeks as the sun will emit over its entire 10 billion year lifetime. But supernovae aren't just spectacular, they shape galaxies. The explosion ejects material at high speeds, creating shockwaves that sweep through surrounding gas. These shockwaves can trigger new star formation by compressing nearby clouds, or they can heat and disperse gas, preventing star formation. In dwarf galaxies, multiple supernovae can blow out the gas entirely, quenching star formation for millions of years. Supernovae also enrich galaxies with heavy elements, carbon, oxygen, iron, and others forged in stellar cores, and the explosion itself. These elements mix into the interstellar medium, eventually forming new stars and planets. Without supernovae, the universe would contain only hydrogen and helium. Planets like Earth, made largely of heavier elements, wouldn't exist. Supernovae are destructive, but they're also creative, recycling stellar material and driving galactic evolution. They're essential players in the cosmic cycle of death and rebirth. How black holes influence their galaxies. Supermassive black holes lurk at the centers of most large galaxies. And they're not just passive residents. They actively influence their host galaxies. When a black hole feeds on surrounding gas, it emits enormous energy, sometimes outshining the entire galaxy. This is an active galactic nucleus, or AGN. The energy released, in the form of radiation, jets, and winds, can heat nearby gas, preventing it from cooling and forming stars. This feedback mechanism regulates star formation, potentially explaining why massive galaxies don't grow even larger. Without black hole feedback, gas would cool and form stars continuously, creating galaxies far more massive than observed. Black holes also influence galaxy mergers. When two galaxies merge, their central black holes eventually spiral together, coalescing into a single, more massive black hole. This process releases gravitational waves and can redistribute stars and gas throughout the merged galaxy. Observations show correlations between black hole mass and galaxy properties. Larger black holes reside in more massive galaxies. This suggests black holes and galaxies co-evolve, their fates intertwined. Despite occupying only a tiny fraction of a galaxy's volume, supermassive black holes wield outsized influence over galactic evolution. Jets of energy from galactic centers. Some supermassive black holes produce jets, narrow beams of particles and energy shooting outward at near-light speed. These jets can extend for hundreds of thousands, or even millions of light years, far beyond the galaxy itself. They're powered by the black hole's accretion disk, where magnetic fields twist and accelerate particles to incredible speeds. Jets are visible across the electromagnetic spectrum: radio, optical, X-ray, glowing as particles spiral around magnetic field lines. Where jets plow into the surrounding intergalactic medium, they create enormous lobes of radio emission, sometimes larger than the host galaxy itself. Jets transport energy from the black hole to the galaxy's outskirts and beyond, affecting star formation and heating gas. They can even influence neighboring galaxies. Observing jets teaches us about extreme physics, magnetic fields, particle acceleration, relativistic motion. Some galaxies, called blazars, have jets pointed directly at Earth, making them appear extraordinarily bright. Jets are one of the universe's most powerful phenomena, reminders that black holes aren't just gravitational traps, but engines capable of shaping their cosmic neighborhoods on vast scales. Quasars and their dazzling power. Quasars are among the brightest objects in the universe, supermassive black holes feeding voraciously, surrounded by glowing accretion disks. They're so luminous that a single quasar can outshine 1,000,000,000,000 stars. We see them mostly in the distant universe, billions of light years away, meaning they were common when the universe was younger. Back then, galaxies were merging frequently, funneling gas towards central black holes and triggering these intense feeding frenzies. Quasars emit across the spectrum: radio, infrared, visible, ultraviolet, X-rays. Their light is so intense, it can ionize gas across millions of light years. For decades after their discovery in the 1960s, quasars were mysterious. Their appearance, star-like points of light, belied their true nature as the energetic cores of distant galaxies. Only later did astronomers realize they were powered by supermassive black holes. Quasars represent a phase in galactic evolution, a time when black holes grew rapidly by consuming vast amounts of material. Modern galaxies rarely display such activity. Their black holes are quiescent, underfed. But in the young universe, quasars blazed brilliantly, cosmic beacons visible across billions of light years. The quiet death of a galaxy. Galaxies can die, though not with violence. Usually, they simply fade away. Death comes when star formation ceases. Without new stars, a galaxy's light gradually dims as existing stars age and die. Massive, bright stars go first, leaving only smaller, dimmer ones. Over billions of years, the galaxy reddens and fades. Why would star formation stop? The gas might be consumed entirely, converted into stars, or locked in stellar remnants. It might be heated and blown away by supernovae and stellar winds, or external processes, ram pressure, stripping in galaxy clusters, tidal interactions, might remove the gas. Once gone, star formation halts. The galaxy enters a quiescent phase, sometimes called red and dead. It's not literally dead. Stars still shine, but it's no longer growing or evolving significantly. Many elliptical galaxies are in this state, having exhausted their gas billions of years ago. They'll persist for trillions of years, gradually dimming as stars burn out. Some galaxies can be revived if they acquire new gas through mergers or accretion, reigniting star formation. But for many, quiescence is permanent, a slow, peaceful fade into darkness. Galaxies that no longer form stars. Throughout the universe, many galaxies have ceased forming stars. These quiescent galaxies are common, especially in dense environments like galaxy clusters. They appear red and smooth, lacking the blue, patchy appearance of star-forming galaxies. What happened to them? Often, environment is the culprit. In clusters, galaxies move at high speeds through hot intracluster gas. This creates ram pressure, like wind resistance, that strips away the galaxy's gas, cutting off star formation. Tidal interactions with neighbors can also remove gas or heat it, preventing it from collapsing into stars. Once gas is lost, star formation ceases within about 1 billion years, as massive stars die and aren't replaced. Isolated galaxies can also become quiescent if they exhaust their gas, or if feedback from supernovae and black holes heats and expels remaining material. Quiescent galaxies are numerous today, but they were rare in the early universe when gas was abundant and star formation vigorous. Their prevalence now suggests most galaxies eventually stop forming stars, settling into a long, quiet decline. Their galactic retirees pass their productive years, coasting toward an uncertain future. The journey of rogue stars. Not all stars remain with their birth galaxies. Some are ejected, flung into intergalactic space by gravitational interactions. This can happen during galaxy mergers, when close encounters with other stars or black holes accelerate a star beyond escape velocity. These rogue stars, sometimes called hypervelocity stars, travel through the vast darkness between galaxies, orphaned from their homes. In galaxy clusters, significant populations of intracluster stars drift between galaxies, stripped from their original hosts by tidal forces. They wander the cluster, bound to the collective gravitational field, but not to any single galaxy. These stars are difficult to detect, isolated and faint against the backdrop of space, but observations confirm they exist, their light contributing a faint glow throughout clusters. For a star to be ejected is rare, but not impossible. Imagine being a star in a galaxy that merges with another. The gravitational chaos might hurl you outward, sending you on a lonely journey through intergalactic space. You'd see no nearby stars, no galactic disk, just darkness punctuated by distant galaxies. It's a solitary fate, a reminder that not everything remains where it began. How galaxies lose their gas. Gas loss is critical to galactic evolution. Without gas, star formation stops, and galaxies fade. Several mechanisms remove gas. Ram pressure stripping occurs when a galaxy moves through hot gas in a cluster. The pressure strips away the galaxy's cooler gas, like wind blowing petals off a flower. Tidal interactions during close encounters or mergers can pull gas out of galaxies, flinging it into space. Supernova and stellar winds heat gas, sometimes to temperatures so high it escapes the galaxy's gravity entirely, a process called galactic winds. These winds can be powerful, expelling gas at hundreds of miles per second. Active galactic nuclei also contribute, their energy heating and ejecting gas from the galaxy's center. In some cases, gas isn't lost, but simply becomes too hot to form stars, hovering in a hot halo around the galaxy. Even without removal, a galaxy can exhaust its gas by converting it all into stars over billions of years. Each mechanism plays a role, and often multiple processes work together. Gas loss transforms galaxies. ending their star-forming days and pushing them toward quiescence. Interactions that tear galaxies apart. Galaxies can be fragile when subjected to strong gravitational forces. Close encounters with larger galaxies create tidal forces, differential gravity, that pulls one side of a galaxy more strongly than the other. These forces stretch and distort the smaller galaxy, sometimes tearing it apart entirely. We see examples throughout the local group. The Sagittarius dwarf elliptical galaxy is being shredded by the Milky Way, its stars strewn along a stream, wrapping around our galaxy. The Magellanic Stream, a ribbon of gas trailing the Magellanic Clouds, shows tidal stripping in action. Over time, these smaller galaxies will be completely absorbed, their stars and gas incorporated into the Milky Way. Tidal destruction is common. Many satellite galaxies suffer this fate, unable to resist their host's gravity. The process takes hundreds of millions to billions of years, gradual but inexorable. For the doomed galaxy, it's a slow dissolution, stars peeled away, layer by layer, until nothing remains. For the larger galaxy, it's nourishment, adding mass and complexity. Galactic cannibalism shapes the universe, building large galaxies from the remains of smaller ones. The tidal bridges of colliding galaxies. When galaxies collide or pass close together, gravity pulls streams of stars and gas outward, creating tidal tails and bridges, graceful arcs stretching between the interacting galaxies. These structures can extend for hundreds of thousands of light years, visible in images as faint, ethereal filaments. The mice galaxies, two spirals caught mid-collision, display long tidal tails streaming behind them. The antenna galaxies show similar features, their collision triggering intense star formation. Where gas clouds collide, tidal bridges connect the galaxies temporarily, matter flowing between them before the structures disperse or the galaxies merge completely. These features form because different parts of each galaxy experience different gravitational forces during the encounter. The side facing the other galaxy feels stronger pull, while the far side feels less. This differential force stretches the galaxy, pulling matter into tails. Computer simulations reproduce these structures beautifully, confirming our understanding of galactic interactions. Tidal features are transient, lasting just tens to hundreds of millions of years before fading. But while they exist, they're stunning, cosmic sculptures shaped by gravity, testaments to the dynamic, interactive nature of the universe. The beauty of galactic mergers. There's a strange beauty in destruction, and galactic mergers exemplify this. Two galaxies, each containing billions of stars, colliding over hundreds of millions of years. It's chaos, but choreographed chaos, following gravitational laws with mathematical precision. Merger images show distorted spirals, twisted arms, glowing bridges of stars. Regions of intense star formation light up in blue and pink, where gas clouds compress and ignite. The violence triggers creation, new stars, new clusters. Eventually, the merger concludes, and a new galaxy emerges, different from either predecessor. Sometimes it's elliptical, its ordered structure scrambled. Sometimes it's a peculiar galaxy, unique and irregular. Mergers aren't rare. Most large galaxies have experienced multiple mergers throughout their history. The Milky Way's bulge and halo likely formed from early mergers with smaller galaxies, and in roughly 4.5 billion years will merge with Andromeda. Observing mergers at different stages gives astronomers insight into the process. Each interaction is different, shaped by the galaxy's masses, speeds, and orientations, but all share one quality. They're transformative, reshaping galaxies and influencing their evolution for billions of years afterward. They're cosmic alchemy, turning two into one. Cosmic dust and hidden light. Dust pervades galaxies, not household dust, but tiny grains of silicates, carbon, and other materials created in stars and spread through space. This cosmic dust absorbs visible light, dimming and reddening stars behind it. In edge-on spiral galaxies, dust lanes appear as dark ribbons across the disk, blocking our view of stars beyond. But dust doesn't just absorb, it also radiates. Heated by starlight, it glows in infrared wavelengths invisible to our eyes. This means dusty galaxies, especially those undergoing intense star formation, shine brightly in infrared, but appear dim or hidden in visible light. For decades, astronomers underestimated star formation rates because dust concealed much of it. Infrared telescopes, like Spitzer and now James Webb, revealed the hidden universe, galaxies forming stars at prodigious rates, their light trapped and reprocessed by dust. Dust also plays a role in star formation itself, helping gas clouds cool and collapse. It's both obstacle and enabler, hiding and revealing, essential to the complex ecology of galaxies. Understanding dust is crucial to understanding galaxies fully. How infrared reveals the invisible. Infrared light penetrates dust that blocks visible light, revealing what's hidden. This makes infrared astronomy essential for studying galaxies. Young stars, buried in the dusty clouds where they form, shine brightly in infrared. So do dusty, star-forming galaxies, billions of light years away, whose visible light is absorbed and re-emitted as infrared. Infrared also reveals cool objects, brown dwarfs, planets, cold dust clouds that emit little visible light. The James Webb Space Telescope operates primarily in infrared, specifically designed to study the early universe. High redshift galaxies, whose light has been stretched into infrared by cosmic expansion, are invisible to optical telescopes, but clear to Webb. Infrared observations have transformed our understanding of star formation, showing that much more was hidden than previously thought. Galaxies that appeared quiet in visible light blazed in infrared, revealing intense star formation obscured by dust. Infrared is a window into hidden processes, a way to see through the veils that conceal some of the universe's most interesting phenomena. It's a reminder that reality extends beyond what our eyes can perceive, and technology expands our senses, revealing deeper truths. The story of the observable universe. The observable universe is the region of space from which light has had time to reach us since the Big Bang. It's a sphere centered on Earth, about 93 billion light-years in diameter. Beyond that boundary, light hasn't had time to reach us yet. Not because nothing is there, but because the universe is only 13.8 billion years old. Light from more distant regions is still traveling, and we'll see it eventually, assuming the universe's expansion doesn't accelerate too fast. The observable universe contains everything we can currently see, all observed galaxies, stars, and cosmic structures. But it's not the entire universe, just the portion accessible to us. The full universe might be infinite, extending forever beyond what we can observe. We'll never know for certain. Within the observable universe, there are an estimated 2 trillion galaxies, each with billions to trillions of stars. It's a staggering number, almost incomprehensible. And yet, it's a boundary defined by time and light speed, not by any physical edge. The observable universe expands as light from more distant regions reaches us, gradually revealing what was previously beyond our view. How many galaxies exist? Estimates suggest there are around 2 trillion galaxies in the observable universe. That number comes from deep surveys like the Hubble Deep Field, which observed tiny patches of sky for extended periods, counting galaxies and extrapolating across the whole sky. 2 trillion is almost beyond comprehension. If you tried to count them, one per second, it would take over 60,000 years. And that's just the observable universe. The full universe might contain vastly more. What's remarkable is how recently we revised this estimate upward. Just a decade ago, we thought there were 100 to 200 billion galaxies. Improved telescopes and analysis methods revealed we'd significantly underestimated. It's humbling and awe-inspiring. The universe is far richer, more complex, more populated than we realized. Each galaxy contains millions to trillions of stars, and many stars host planets. The numbers spiral into the realm of fantasy, yet they're rooted in careful observation and rigorous extrapolation. We live in a universe that's almost incomprehensibly vast, part of an island of billions of other islands, each floating in an infinite sea of space. The knowledge should dwarf us, should make us feel small, and perhaps it should. But there's also something magnificent about living in such a universe, about having the capability to contemplate it and count our neighbors, counting the billions in the sky. Astronomers estimate galaxy counts using a technique called galaxy surveys. Telescopes observe patches of sky, counting galaxies and measuring their distances through redshift. From these samples, they extrapolate to the entire sky, calculating how many galaxies exist across the whole observable universe. The Hubble Deep Field, observed in 1995, was transformative. Astronomers pointed Hubble at a tiny patch of seemingly empty sky, just 1/13 millionth of the celestial sphere. After 10 days of exposure, the image revealed about 3,000 galaxies, extrapolating across the entire sky. This suggested roughly 100 to 200 billion galaxies existed. But later surveys, particularly from the Sloan Digital Sky Survey and Hubble's successive deep field images, refined and revised upward these estimates. And recently, studies accounting for galaxies too faint to detect directly suggested the true number is closer to 2 trillion. Each revision required developing better analysis methods and acknowledging selection biases. Distant, faint galaxies are harder to detect, so earlier surveys underestimated their abundance. Modern surveys account for this, painting a more complete picture. Counting galaxies is ongoing work, and future telescopes will refine estimates further. But the basic message remains: the universe is far richer than we can directly perceive. The expanding universe. The universe is expanding. Space itself is growing, carrying galaxies farther apart over time. This wasn't obvious until the 1920s, when Edwin Hubble made observations suggesting distant galaxies were receding from us. This was revolutionary, overturning the assumption of a static universe. Hubble found that more distant galaxies were receding faster, a relationship now known as Hubble's law. This expansion doesn't mean galaxies are moving through space like objects traveling across a landscape. Rather, space itself is stretching, and galaxies are carried apart by this cosmic expansion. Imagine a balloon with dots representing galaxies. As the balloon inflates, the dots move apart, not because they're traveling through the balloon's surface, but because the surface itself is expanding. Expansion is the same throughout space. Every galaxy sees other galaxies receding. There's no center to the universe, no preferred location. All points see themselves as centers. This is a profound realization, one that displaced humanity from any special cosmic position. Expansion has consequences. Light from distant galaxies is stretched into longer wavelengths, shifted toward red. It also means the universe was denser in the past, eventually leading to the conclusion that it had a beginning, the Big Bang. How galaxies drift apart over time. As space expands, galaxies drift apart, moving to greater distances, even without any local motion. A galaxy 1 billion light-years away is receding at a speed determined by Hubble's constant, about 45 miles per second per billion light-years. Over cosmic history, this accumulates. A galaxy that was 100 million light-years away when the universe was young is now billions of light-years distant. This isn't motion through space, but rather the stretching of space itself. Locally, gravity can overcome expansion. Our local group of galaxies will remain gravitationally bound. The Milky Way and Andromeda will collide and merge. But on larger scales, expansion dominates. Distant galaxy clusters recede from us faster than new light can reach us, eventually crossing an event horizon beyond which we can never see them. The universe is becoming progressively more sparse, galaxies separating forever. In the very distant future, trillions of years hence, observers in our region will see almost no other galaxies, each having receded beyond the cosmic horizon. It's a sobering thought, the universe gradually emptying as galaxies drift apart, isolated and alone, watching their universe darken. The redshift of distant galaxies. Redshift measures how much light from distant objects is stretched by cosmic expansion. When space expands, the wavelengths of light expand too, shifting toward longer, redder wavelengths, hence redshift. A galaxy with redshift z equal sign 1 has light wavelengths stretched to twice their original length. For z equal sign 10, stretching is 11-fold. Redshift directly relates to distance. More distant galaxies have larger redshifts. By measuring a galaxy's redshift, astronomers immediately know its distance. Redshift also tells us the expansion history of the universe. By measuring many galaxies' redshifts and distances, we can trace how fast the universe has expanded at different times. This revealed a profound discovery. Expansion is accelerating. In the 1990s, observations of distant supernovae showed the universe's expansion rate is increasing, not decreasing, as gravity should cause. This acceleration is attributed to dark energy, a mysterious component making up about 68% of the universe's total energy density. Dark energy acts opposite to gravity, pushing space apart faster and faster. Its nature remains unknown, one of physics' greatest mysteries, but redshift measurements continue revealing its effects, shaping the universe's fate. What the oldest galaxies tell us. The oldest galaxies, forming within the first billion years after the Big Bang, carry information about the early universe. These galaxies were smaller than modern ones, more chaotic, intensely forming stars. Their chemical composition, almost pure hydrogen and helium, reveals they contain no heavy elements yet. The earliest stars were made of primordial material, creating the first generation of elements when they exploded. By studying ancient galaxies, we learn when the universe's dark ages ended, and the first galaxies lit it up. We discover how quickly structure formed, how fast supermassive black holes grew, how efficiently stars formed in the early universe. We see the universe evolving from a near featureless state to the complex structured cosmos we observe today. James Webb's observations of these ancient galaxies are rewriting our understanding. Some are more massive than expected, suggesting star formation was more efficient than thought. Some show structure, bars, bulges, implying organization emerged quickly. These distant ancient galaxies are windows into a universe we'll never directly access except through light that's been traveling for eons. In them, we see our cosmic origins. The fate of all galaxies. All galaxies have fates determined by cosmic evolution and dynamics. Some are already dead, their star formation long ceased. Others are still young, forming stars actively. But eventually, all will fade. Within the local group, the Milky Way's fate is to eventually merge with Andromeda and possibly absorb other dwarfs. In galaxy clusters, central galaxies consume neighbors, growing larger, while smaller galaxies are tidally disrupted and absorbed. Over time, clusters settle, with one or two giant ellipticals dominating. On cosmic scales, expansion will eventually isolate remaining galaxies from one another. Billions of years hence, the universe will be so dilute that interactions are rare. Existing galaxies will quietly age, stars gradually burning out. The universe will grow darker and colder. Eventually, after timescales of 10 circumflex, 14 years or more, stars will die, planets will cool, and the universe will approach its final state, a thin fog of elementary particles drifting through infinite cold space. It's a distant future, but the trajectory is clear. Galaxies are temporary, brilliant structures burning against entropy. They transform raw material into light and complexity for a time, then slowly fade. When stars fade and darkness spreads, billions of years from now, stars will begin to die faster than they're born. Star formation has already declined from its peak about 10 billion years ago. Eventually, it will cease almost entirely as remaining gas is consumed or driven away. Without new stars, old ones will burn out. First the massive bright ones, then progressively smaller stars. The oldest red dwarfs, dim and long-lived, will persist the longest, burning for trillions of years. But eventually, even they'll exhaust their fuel. Galaxies will fade from blue and white to orange and red as young stars disappear, then increasingly red as older stars die. Finally, they'll emit only faint red and infrared light, then fade below detection. The universe will darken, planets will cool, orbiting cold stellar remnants, white dwarfs, neutron stars, black holes. Life, if it still exists, will struggle in the cold darkness. The cosmos will become quieter, less dynamic. Instead of galaxies blazing with stars, there will be isolated, dark remnants, stellar ghosts, orbiting in the vast void. It's a melancholy vision, but it's the universe's ultimate trajectory if it continues expanding forever. The heat death of the universe. Heat death is the universe's predicted final state, maximum entropy, complete thermodynamic equilibrium, everything at the same temperature and unable to change. In this state, all available energy is dissipated. Stars have died, black holes have evaporated through Hawking radiation, and all matter has decayed to its most stable forms. The universe is uniformly dark and cold, expanding forever into eternity. Heat death doesn't happen suddenly, but through an unimaginably long process. The timescale isn't millions or billions of years, but 10 circumflex, 100 years or more, a number so vast it dwarfs comprehension. We're talking about a future so distant that the current age of the universe is negligible by comparison, but the direction is inexorable. If the universe continues expanding and entropy continues increasing, this is where it leads. Some physicists imagine even more distant futures, 10 circumflex 1,000 years and beyond, where bizarre processes occur that we haven't predicted. But for practical purposes, heat death represents the end. The universe, which began in a state of extraordinary order, the Big Bang, will end in complete disorder, all energy unavailable to do anything. It's a profound asymmetry, suggestive of something deep about the universe's nature. What will remain after everything ends? In the universe's far future, what persists? Possibly nothing. If all matter decays and all radiation spreads to infinity, the cosmos becomes empty, but there are speculative possibilities. Some theories predict stable remnants, isolated protons, black holes, strange matter, persisting indefinitely. Others imagine quantum fluctuations, creating new universes from the vacuum. From our perspective, nothing remains. All galaxies have dispersed beyond the cosmic horizon. All stars have died. All planets are cold. No observers remain to witness the cosmic ending. Life, tied to stars' energy, will have vanished long before. Even complex chemistry, atoms bonding, becomes impossible in the cold, dilute universe. Only the simplest particles persist, if anything does. It's a sobering endpoint, but also curiously beautiful in its quietude. The universe, after an age of activity, returns to something like its initial state, simple, sparse, featureless. Perhaps, in some deep sense, this represents a cosmic return, a completion of a cycle that began with the Big Bang. Or perhaps, the future holds surprises we can't foresee. Either way, the far future remains mysterious, unknowable, a frontier of speculation beyond our current reach. Galaxies, as cosmic memories. Galaxies are more than just collections of stars. They're cosmic memories, records of the universe's history. Each galaxy's form, color, and composition tell stories. Spiral galaxies record the universe's youth, still forming stars, still evolving. Elliptical galaxies are survivors of cosmic mergers, their histories written in their smooth, featureless appearances. Tidal tails and bridges show recent interactions, evidence of encounters that occurred in the past few 100 million years. The oldest galaxies carry light from the universe's infancy, letting us observe conditions billions of years ago. Supernova record moments of stellar death and transmutation of elements. Black hole jets reveal the universe's most extreme physics. Every galaxy is a library, and every feature a page in the cosmic story. By studying galaxies, we read the universe's autobiography, learning what it was like in its youth, how it has evolved, what it will become. We're detectives piecing together clues scattered across billions of light years and billions of years of time. The clues are imperfect. Light years of distance blur details, and time stretches understanding. But in aggregate, galaxies tell a coherent tale of cosmic evolution and transformation. The beauty of infinite space. There's a peculiar beauty in infinity, in the endless expanse of space, filled with galaxies that stretch beyond comprehension. It's not a beauty of comfort or familiarity, but of wonder, of awe at scale and scope that dwarfs human significance. When we contemplate the night sky, even in our local neighborhood, with visible constellations and bright stars, we touch this feeling. And when we extrapolate to billions of galaxies, each with billions of stars, the magnitude becomes vertiginous. Space is beautiful precisely because it's vast, complex, and largely indifferent to human concerns. It humbles us, putting our daily worries in perspective. It inspires us, driving the curiosity that builds telescopes and sends spacecraft to explore. It connects us to something larger than ourselves, something that has persisted for billions of years and will continue for billions more, with or without humanity. In that infinity, there's also loneliness, the vast distances separating galaxies, the isolation of individual worlds. But there's companionship too, in the knowledge that we're part of something vast, connected by gravity and history to every star and every galaxy. Space is beautiful in its emptiness and in its abundance. The endless journey of the stars. Stars continue their endless dance, orbiting galactic centers, moving through space, burning their fuel billions of years at a time. Their journey is measured in cosmic timescales. Billions of years to build, billions to shine, billions more to fade. Each star is small, temporary, but collectively they light the universe, enable planets, create elements, and sustain what wonders exist. Our sun is one such star, unremarkable in size or brightness, yet profound in that it enabled life here on Earth. It will persist for another 5 billion years, then expand and cool, likely consuming our world, but countless stars will continue afterward, burning long after Earth is dust, and those stars will slowly die, their light fading into darkness over timescales of trillions of years. Yet even in dying, they matter. They enrich the cosmos with heavy elements, scatter their ashes to create new stars and planets, contribute to the universe's complexity. Stars are the universe's primary actors, the engines driving cosmic evolution. Their endless journey continues regardless of observers. It's a play acted on a stage empty of audience, yet performed with the utmost beauty. In that journey, we find meaning, not because we're central to it, but because we're part of it, participants in a cosmos far grander than ourselves.